Good morning, everybody. I have a couple updates up here. Again, we have these silly board lights that won't turn off. I don't know why the lighting is such a stupid problem this semester, but I cannot get these lights to turn off, so it's a little bit hard to see. But midterm one's next Monday. It's Monday evening, 6 p.m., Hitchcock Hall, 131, big lecture room. This room, two things I don't like about this room. One, the lighting isn't great, but the second thing is the desks are kind of small. You're going to be taking your exam on a device. You get your choice of device. You can use an iPad, you can use a laptop. I would probably recommend an iPad just so you can easily move it aside so you can write some work onto a scratch paper pad that we'll give you so that you can write some work out as you go on the test. On your iPads, you're going to have to use a lockdown browser, so you're not going to be able to use a pencil on the iPad. You're not going to be able to write on your screen during the test, but we're going to give you a sample paper booklet that you can write your work onto so you can do your calculations that you need to do for the test. We collect them, but we don't grade the scratch paper booklets. We simply collect them so that you're not writing the questions down on the test to give to people in the future who might take the test. I think our tests go on Monday, Tuesday, and Wednesday night next week, and we're in the group that goes first. So we want to make sure that those Tuesday people don't find out what's on the test. But practice midterms are going to post soon. Try to use those midterms once you've completed reviewing chapters 1 through 3. So I don't think it's going to be suitable to take a practice exam probably until the end of the week, maybe into, say, Friday-ish. Until then, I think using those daily practice quizzes that I have is a good way to get some feedback, a good chance to get some study problems. There's a lot of homework problems in the book. I don't necessarily think a lot of those homework problems are great to do, but you can go to the end of chapter problems if you're looking for extra problems to do. If you look at the red shaded problems in the end of chapter problems, they're answered in the end matter in the book, so you can check the answers. I think they're actually hyperlinked in the e-text. Should take you to the answer so you can check your work. And then the test does cover chapters 1 through 3, and the mostly multiple choice questions. You'll see on the practice exams that there's a few questions that'll be like data entry, where it'll ask you a math question, and you have to enter your answer into Carmen, the method you're going to be taking your midterms. So just know that there will be on the real exam some data entry questions. When you get to a data entry question, be careful to read. It'll usually say enter your answer to the nearest point X decimal place to the tenths place, or enter it to the hundredths place, depending on the particular problem. Those questions are not grading sig figs. If you're worried, if you're looking at those math questions that we ask, those are kind of standalone problems that aren't checking sig figs along with your actual answer. So we're just looking for your answer. The program's finicky, wants answers recorded to a specific decimal. So even if your answer is let's say 5, and it says to record it to the nearest, it'll say record it to the nearest point XX, and you have to put 5.00. And for some reason it wants you to put those zeros. Okay, so just know that this lockdown browser is required. There was an announcement set on Friday afternoon from Sophie White, our course coordinator. Check out that email. Whatever device you plan to take the test on, make sure to download that lockdown browser. There's a test that you can do to make sure that your device works. In the past, everybody had an iPad in the course, so in the past, everybody used an iPad. It was a little bit easier to start a test when we knew this, everybody had the same device. But I would recommend the iPad because we know some of the nuances of the iPad better than random laptops. Okay, back into chapter 3. This is kind of the next problem that we were coming to in the notes, was just taking a particular mass sample of water and then doing a couple calculations with it. So this is getting into the topic of going from a mass to moles. We can make this conversion here. We use a molar mass. We'll look up the molar mass or use a periodic table to get that molar mass. We can then calculate the moles into the unit, such as a molecule being the main example, that how many molecules are there in a particular sample. Well, that's going from moles to that unit going to molecules. This is usually using Avogadro's number. Na is usually our symbol for Avogadro's number. .022 times 10 to the 23 is Avogadro's number. Now, as we get close to the exam, a question I'll get is, well, what information do you get on the midterm? once you get the practice midterms, you can see what information is provided there. If you go to my daily quiz page, I have like a supplemental info chart. It's actually very lengthy. I've been trying to get the department just to put that onto the midterms because it'd be so much easier. But if you look at that chart, you'll see a tremendous amount of information, and then there's some highlighted info, and the highlighted info is what you would get on a test if you need it. Your equation sheet for the test, or your like supplied information sheet, there'll be like 5 things on there. Just a couple things that they give you on most tests. But then we'll supplement information within a problem if you need more information. For example, if you need a kilogram to pound conversion, we'll give you that. We don't expect that you have that memorized. There's almost no conversion factor that we expect that you have memorized. We even give you on the test 1 cubic centimeter is 1 milliliter, which I think is pretty obvious, but we give you that one just to make sure you have that conversion factor. The conversion factors you don't get are the prefix conversions, like the milliliter to liter, gram to kilogram. Those are, using the prefixes, those are the conversion factors that you have to know. Okay, so let's get into this question here. Number of moles of water, how many moles are present? Well, I use dimensional analysis, start with our 100-gram sample. We have to go from grams of whatever that is, so water, using its molar mass, the grams per mole. So I look up the grams of water per mole using the periodic table. So we can take the 1.008 for hydrogen times 2. We can take the oxygen 16, add them together. Kind of pretending I'm doing the calculation. I know it's 18.02. And so it's 18.02 grams per mole of water. And so I'm getting this here just from our periodic table. And then we can think of that number, 18.02, being AMU per 1 molecule, the atomic mass units for 1 molecule of water, or the grams per 1 mole of water. And the mole of water is that Avogadro's number of water molecules. And so if we start our calculation here, 100 divided by 18.02 is 5.549 moles of water. Now, how many water molecules are present? So how many molecules of water are there in a 100-gram sample? Now, the one thing that sometimes gets tricky, if we're running mole, and a mole is specifically an Avogadro's number of the particle, and then we're running molecule, we have to sometimes be careful with our abbreviations so that we don't abbreviate molecule and think that it's also the mole. So a molecule, I might abbreviate it with the C and just be very careful to think, now a molecule is just 2 hydrogens, 1 oxygen, and that's simply just one of those molecules is what we're thinking of our molecule. So the number of molecules of water, I'll start with the 5.549 moles that we just calculated, and then just use Avogadro's number. So 1 mole of X is an Avogadro's number of X, so 1 mole of water molecules is an Avogadro's number of those molecules. So I'm multiplying this by 6.022 times 10 to the 23. So I get 3.342 times 10 to the plus 24 molecules of water. So when we have a reasonably large sample, we have like 100 grams of water, we should expect there to be a tremendous number of water molecules, and of course that's what we have here. Like if we were to do this calculation, sometimes we get things backwards. Like let's say we flip this conversion factor by accident. Often, what's the easiest way to flip a conversion factor? It's probably by not writing out your work, or by not writing out the units, or not trying to make sure we're canceling out our units. So if we're not doing our math meticulously, it's easy to interconvert, maybe divide where we expected to multiply, and then we get something times 10 to the minus 24. Well, that's an incredibly small number of molecules for the sample. So sometimes if we're just mindful of how big or small a number should be, we can catch a mistake like that. Now, how many hydrogen atoms are in the sample? We said, well, I have 3.342 times 10 to the 24 molecules of water. How many H atoms are present within that sample? Because each water molecule contains 2 hydrogen atoms. So 1 molecule of water contains 2 H atoms. So every 1 water contributes 2 H atoms. So they're still attached to the oxygen. We're not saying like how many free H atoms are there in the sample. We're just saying if you just looked at the sample and said, how many hydrogen atoms total are present here where every 2 of them are bonded to one O, we would just use the formula. So the number of H atoms in this sample, we would just take our 3.342 times 10 to the 24 molecules of water. And just use every 1 molecule of water contains 2 H atoms. So we can go from our unit to atoms using the formula. So inspecting the molecular formula allows us to see 2 H atoms per 1 O. So we just double to 6.684. Times 10 to the 24 hydrogen atoms. Now in this 100-gram sample, how many of the grams in that sample are due to the H atoms, where the remainder would be due to the oxygen atoms? Well, there's 2 ways I can probably think through this problem here. One would be just, well, what does this collection of H atoms weigh? What's its mass? So we could say, well, the number of grams of hydrogen from that collection we just have to kind of go backwards into maybe moles, or maybe we use an AMU conversion and then convert AMUs to grams. So let me do it that way. Let me use the mass that 1 H atom from the periodic table has a mass of 1.008 atomic mass units. To kind of go back to the other way, like our atomic weights are either AMU per atom or grams per mole of the atom. So let's use the AMU here. And then the next step we would do is just the AMU to gram conversion. And the AMU to gram conversion is just another Avogadro's number. So it's an Avogadro's number of AMU Avogadro's number of AMU, so 6.022 times 10 to the 23 AMU. I almost got confused, but I'm just converting AMU into gram. So we've canceled out the H atom, canceled out the AMU, converted over to grams. So I get 11.19 grams. So about 11%, well, specifically 11.19% of the mass is due to hydrogen. Now I mentioned there's maybe another way, and almost some of these problems, you can write the steps out in a couple of different ways, or you could think of maybe a slightly different way to solve the problem. A second way we could solve this final problem might be to say that the grams of hydrogen, so a second approach we might take is maybe we could just have said, well, let's take the 100-gram sample that we started with, just go back to that mass, and just multiply this by the percent mass of H in the compound. And we were talking about percent masses last time, where the percent mass of hydrogen in water would be the mass of hydrogen in the formula divided by the formula weight. So the percent by H, at this value here, would be equal to 2 times 1.008 for the two H's in the formula, divide by the formula weight of water, times 100% for the percentage, and that should probably be 11.19%, but just to check, that's precisely what we get. Multiply that by 100, and we get the same 11.9 grams. So you might have been thinking to yourself, well, why are we dividing by Avogadro's number when I could have just done 100 times 2.016 divided by 18.02? That works as well. So most problems that we do in this class, there's going to be more than one way to correctly get the right answer, and that's part of the problem is just understanding how you can use the concepts that we're teaching you to solve these types of problems. Now there's this problem here. I'll throw this to you guys here. I'm just going through a given sample where we have magnesium nitrate. We give you the formula. You might think everyone thinks we're super hard. We try not to be overly hard. We don't want to put nomenclature into every question. Sometimes we've done this, like maybe once or twice in the past, or some instructors have thought, wouldn't it be great in this problem to not give you the formula? So we would test you on our nomenclature that magnesium is Mg2 plus, nitrate, of course, is NO3 minus, and of course we'd have to have 2 nitrates to balance out the charge. But oftentimes you'll see, we'll give you a name and the formula so that we're not tripping you up on naming within this topic here. But we have 4.72 grams of magnesium nitrate. We just want to know how many nitrogen atoms there are present within the sample. So why don't I give you guys 2 or 3 minutes to work on this. Feel free to work with each other if you wish. So those of you with answers, do you want to check with your neighbors and kind of see if you guys agree? All right, so I saw you guys diligently working. I really like seeing that because sometimes these problems, I mean, this one's maybe, like, I don't know from your guys' vantage point, it's hard for me to know what's easy, what's hard, but when I see you guys working and actually working through the problem, setting it up, I know that hopefully we're just reinforcing how we solve a problem like this. We just started our problem, I hope, with what it is we're looking for. Because sometimes if we don't start our dimensional analysis with what we're looking for, maybe we get confused on where we start or stop our calculation. So I just started with what I'm looking for, number n atoms. Begin the math with the 4.72 grams of magnesium nitrate. I use the formula weight, or the molar mass of magnesium nitrate goes to moles of magnesium nitrate. Now this step here, I could have done these two steps almost interchangeably. I could have said there's an Avogadro's number of MgNO32 units per mole of MgNO32, or I could have done it like this. I just looked and said, well, for every 1 mole of magnesium nitrate, there's 2 moles of nitrogen, just from inspection of the formula. So I inspected the formula first, completely fair to do, and that allows me in the next step to use Avogadro's number to go to the number of n atoms. So 1 mole of n contains an Avogadro's number of n. What is n? It's an atom, so Avogadro's number of nitrogen atoms. Sometimes I find that what Avogadro's number goes along with is one of the most confusing parts when you haven't seen this in a while. Just you get the Avogadro's number of whatever it is that you're dealing with. So 1 mole of n is an Avogadro's number of n atoms. If you had in a different problem a mole of CH4, 1 mole of CH4 would be an Avogadro's number of CH4. And what is CH4? It's a molecule, so CH4 molecules. Okay, so when we do the math, we come up with 3.83 times 10 to the 22 nitrogen atoms. Okay. So now, sometimes a problem like this on a test could be a data entry. These days, a lot of these problems are just you got a key in the answer. I don't know if they usually go scientific notation because that gets tricky to enter. I think most of our data entry problems are just ordinary numbers where you're entering 2.25, things like that, without having the result be a number that's in exponential notation. But a lot of times a problem like this might have, after the first step, whatever the answer is, that might be one of the choices. After the second step, that might be one of the choices. If you forget to multiply by 2 here, that might be one of the choices. So these choices here are going to be cleverly chosen such that if you're not entirely sure how many ways, what step you stop in the problem, you might see the choice, you might be tricked into answering. We're not really trying to trick you, we're just trying to make sure that you know the proper steps of the problem and you know how to put them all together. Okay, so let's get into a chemical reaction. We're going to kind of jump ahead into a chemical reaction. We're going to go back into some formula problems. So we kind of take a little bit of a scattered approach here in chapter 3 to try to think about where we're eventually trying to get is picturing what goes on within a chemical reaction so we can quantify the aspects of the reaction. Here we're going to start with a diagram. We'll work this problem out together. So sometimes these problems here with multiple choices I'll throw to you guys, but this one here I think we can just look at this one together. So this is what we call like a particle diagram question. We would show you some collection of the reactants and we try to figure out what the product box might kind of look like, or after the reaction takes place, what might the box kind of resemble or look like. So here we're told to consider N2 by the black spheres and the gray spheres are O2s. So O2s are the gray spheres. So we have our N2 and then our O2. And then we have a reaction taking place where one N2 will react with 2 O2s according to the reaction to produce 2 NO2s. So what's going on during the course of this reaction is you can imagine kind of lassoing out, if you will, a nitrogen and 2 oxygens, and then that they're going to change form. We're going to get a nitrogen bonded to an oxygen. I don't have an easy gray color. I'll just use yellow for the gray. And then we would get another nitrogen, and then the O's here. I'll even change these to like yellow to kind of show that we're taking two of the oxygens and kind of breaking them apart, attaching them to an N, breaking apart the N, taking one N with the two O's, another N with the other two O's. So we've taken what was an N2 and two O2s and turned it into two NO2s. Okay, now can we do it again? So this just kind of becomes, a process of going through however many times we can lasso out two gray spheres and two of the O2s and an N2, and we make this again. So we get two more N2Os. Excuse me, NO2s. So we get two more NO2s, and then we can do it one more time. Now, notice when I lasso out the last grouping that there's one nitrogen. See the one N2 that I couldn't get into the little circle? That there's this one N2 left over. So I'm going to have one N2 that's unreacted just simply because I didn't have enough oxygen around for it to react. So we have one N2 left over, and then I get my two other NO2s. Now, if it's not clear or obvious, these reactants and products are all gaseous. That's kind of why I'm just randomly drawing them in the box. If we had a gas, these particles are just randomly floating around the box. But randomly floating around such that the products have two O's stuck to an N. So it's floating around as an NO2 in that fashion. And so then we have this one N2 left over. So if we count, we produced 6 NO2s in our box. By the reaction that took place, and then one N2 remained. It remains unreacted. Now, why did it remain unreacted? Well, we just had too much of it present. When you carry out a chemical reaction, the reaction might say for every one N, we need, for every one N2, we need two O2s. Well, we can mix together in the laboratory whatever concoction of reactants we want to mix together. It's just if we mix one of them in such a way that it's in excess, there's too much of it, it will be left over after the reaction completes. Within a particle diagram question, you can kind of picture this out. So if you have a small collection of molecules that are reacting, you can probably sketch what's going on, get a picture in your mind that the reaction is just producing 1 to 2 to 2. We're just taking one of the N2s, two of the O2s, and then producing two of the NO2s. Now, once we get to like having 5 grams of this and 10 grams of that, it's going to be pretty hard to think about all the molecules because it's going to be an Avogadro's number, nearly an Avogadro's number, depending on the problem. We can't sketch this out. It would take us quite a while if we wanted to sketch this out for 10 to the 23 molecules. But if we have a couple, we can picture this type of reaction box here. So what we should have after the reaction completes, 6 NO2s in the box, and that one N2 that was unreacted. So after the reaction completes, we have the products that formed, and then any of the reactants that are unreacted that remain. Okay, so that's the basic kind of like one way we can think of a chemical reaction is through like a particle diagram box and picturing the reactants and how they can react to form the products. Now, one thing we don't get is how these reactions go. Like, you might wonder, how is it that N2 breaks apart and the O2 breaks apart and you form these molecules? And some details, those are covered a little bit in chapter 14 later in chemical kinetics, where we try to think mechanistically, like how does a reaction take place? So right now, we have no clue on how these reactions take place. We just know that at the start you had the N2 and the O2s, and afterwards you had the NO2s. And then you had the unreacted starting material. Okay, so how do we know formulas? Like, how do we ever know that a compound has a particular formula? Well, some of the ways are through doing some sort of experimentation. Some of the experiments could be we get a percent mass of the elements within the substance that will allow us to determine the empirical formula. You might remember the boring problem we did where we had CH2O, C6H12O6, and found they had the exact same percent by mass. And the reason why they have the same percent by mass is because they share that same empirical formula. So you might have remembered when we did the CH2O, C6H12O6, that these molecules shared that empirical formula of C to the 1, H to the 2, O to the 1, so they have the same percent by mass. So if you know the percent masses, the best you can get is that simplest ratio of the elements within the compound. We'll do an example of that problem in just a moment. If you know the compound's empirical formula, then you can get the molecular formula. For a molecular compound, that's really what we want to know, is the molecular formula, but we can get a molecular formula from a molecular weight and then from an empirical formula. So if we can do a second experiment to find a molecular weight, one of those is, we may not understand the details of this, but if you remember that mass spectrometry example where that's the one where we were finding, like, for a given element, what are its isotopes that exist as, what are their masses, what are their abundances. That experiment can be done to find the molecular weight of a compound. You can do that experiment along with the percent composition to get a molecular formula. Another topic that we're actually not going to cover this semester, I'm going to show you what the problem looks like because you probably will see the problem. I just want you to see what it looks like to know that you're not going to be responsible for solving it. It's good because this problem will take a while to solve and it buys us some time to review other concepts in the class. But there's a combustion analysis topic in section 3.5 that's discussed. We'll briefly show it, but we won't go through the meticulous details of solving this problem. So that's a third way we could get formula information. Okay, so formula information is usually coming from some experimental data. This is one such example here where we have a question that's saying, well, which formula is consistent with a compound found to be comprised of a mass 36.6% chromium, 12.7% carbon, and oxygen as the remainder, and these are the percent by masses. Okay, so the question would be, well, how do we get at the formula? If you remember these problems, what we want to begin with is some ratio of the masses of these elements. So we want to think the percent by masses, these are kind of give us the mass ratios of these elements, and we just need to go to their mole ratios. And if we can go to the mole ratios, we can then hopefully find the simplest whole number ratios. And so what I start with here is just a ratio of these masses that we know to be true based on the information provided in the problem. So I know that if I have 36.6 grams of chromium within a sample, then the ratio to the mass of carbon should be to 12.7 grams of carbon. And then the remainder is oxygen. So 100% of the sample is these three elements, so I just do 100% minus 36.6% minus 12.7% to get the remainder. As 50.7. And that's the percent by mass, that's oxygen. Now, if you've seen this, well, okay, I bet we've all seen this. Whether we remember seeing it's a different story. So if you forget seeing it, that's fine. But I bet you've seen this type of problem before. And I guarantee you that the first step was assume a 100-gram sample. Who remembers that line, like assume 100-gram samples? Anybody remember that? I see a hand or two, see some hands. Well, you can assume whatever you want to assume here. You just have to assume masses that are true for the information provided in the problem. You just have to choose masses here, the gram to gram to gram. That's true for the 50.7% being oxygen, 36.6% being chromium, 12.7 grams being carbon. The easiest mass to then start with would just be the percentages expressed as grams, i.e. assuming the 100-gram sample. So sometimes in my head, I think for a student, assuming a 100-gram sample is like, well, why would you assume that? Well, you only assume it because it makes the problem easy. It gives us an easy way to start with the mass ratio for those elements that's true based on the information provided in the problem. So we just need to start with masses that go with that same ratio. And if you're with me, we just need to go from the mass ratio, which we have here, to the mole ratio. So we just need to convert these to moles using each of those elements' molar masses. And so we just look at chromium's molar mass. It's 51.996, so we'll call it 52.00. Carbon, 12.01 grams per mole of carbon. Just canceling grams into moles. And then our oxygen, 16.00 grams per mole of O. These problems here are usually one where if you're going to at least like 4 sig figs on your atomic weights, you're going to get an easy way to get your masses right. Sometimes if we round, the way the problem's round will make it tricky. So I just try to use like 12.01. Sometimes like you guys are just using 12, 14, which would probably be okay for most problems. When you end up having to do these ratios, sometimes it's better to be a little more precise so that your ratios are like dead on the whole numbers later and not a little bit off and hard to tell if you can round or not. Okay, so let's actually stop. Let's not do the next step yet. Let's stop and calculate these numbers here and see what these are equal to. So 36.6 divided by 52 is 0.704. I'm actually going to go one more sig fig, 0.7038 moles of chromium. 12.7 divided by 1201 is 1.057. And then 50.7 divided by 16 is 3.169. So then the question is, well, how close do we need to be to a whole number to round? The answer is pretty close. You need to be probably within at least 0.05 to round. So if we're thinking, can we round the chromium to 1? We're too far away to round to 1. So we got to do some work still to get our simplest whole number ratio. So if you're with me, the question is just like, what's the ratio of CR to C to O in this compound? Is it 1 to 1 to 2, 1 to 2 to 3, et cetera? Well, what do you think the next step would be? If we got to find a whole number and we got to keep these as ratios, we got to keep thinking that these are all moles that are in ratio to each other. If we're thinking these are in a ratio to each other, when I do the next step, hopefully it won't be too confusing, then we need to look for the smallest number. It's the 0.7038. We're going to divide all those moles by the smallest number. Why? Well, at least gets us one whole number. At least gives us the mole of 1 for that first number. And then hopefully allows us to either see fractions or hopefully whole numbers in the other position so we can know where to get those ratios. So if I divide by 0.7038, sometimes we forget the details and we divide all of them by themselves and just get 1. That's not what we're doing. We're dividing all of these by 0.7038 to keep the ratio intact. If I divide one by 0.7038 and the other one by a different number, I've broken the ratio. So we get 1 mole of chromium in ratio to 1.057. 0.7038 is 1.502. And then 3.169 divided by 0.7038 is 4.503. Okay, so we're close to whole numbers. I think you can see we want the simplest whole number ratio, and I have, CR to the 1.5 for C and 4.5 for O. So our next step is, well, what's the next multiple? It has to be a whole number. Otherwise, we're not going to get a whole number. If you just if you start thinking, I need to multiply by 2.5, well, you would never get a whole number. We have to multiply here by a whole number. One of them's a 1. So if I multiply by anything other than a whole number, I don't get a whole number for at least one of them. I want whole numbers for all of these. So I start thinking, do I double, triple, quadruple? There's not much of a math step here. I think it just be, sometimes you can see here you double. But sometimes it'll be 1.33 where you triple. Sometimes it'll be 0.25 and you multiply by 4. So you just start thinking, do I multiply them all by 2, by 3, by 4, and you keep going upward until you get whole numbers in every position. So we're going to go with 2. Pretty obviously 2, but then we get 2 moles of chromium in ratio to 3 moles of carbon in ratio to 9 moles of oxygen. Now, we could more precise, like let's look at oxygen real quick, 4.503. Let's just worry about the 0.03 hanging. When I multiply that by 2, I get 9.006. If I do this math here, 9.006, and that's clearly within plus or minus 0.05. We want to be within about 5% of that whole number in order to know that we can round up. So like if you use the right atomic weights in a problem and you're precise with your calculations, you're not rounding too many times prematurely, it'll be pretty clear on where you round to. Okay, so Cr2, C3O9. Now, you probably remember carbonate, of course, so this looks like probably carbonate. And if that's carbonate, we'd go Cr2, CO3, 3. So that's probably the answer in the format it's written over here. Yep, so it looks like answer D. So answer D would be consistent with the formula Cr2, C3O9. Lengthy problem once you start these, I mean, it's lengthy to write all out and say it all. Once you do these problems a couple times, you'll realize you can write this workout in 2 or 3 minutes. So not the longest of problems, but one that's just very meticulous of we start with mass ratios, go to mole ratios, go to a simplest whole number ratio through first dividing by the smallest and then looking for multiples if we don't see whole numbers once we get to this step here. So we didn't see whole numbers, so we found the multiple of 2. Okay. So this compound here is an ionic compound. We mentioned ionic compounds are best represented by that empirical formula of their ions. The simplest ratio of chromium to carbonate here was 2 to 3 for chromium to the carbonate ion. For molecular compounds, it's a little bit more complicated, right? Like we would probably get an empirical formula here and want to know the molecular formula. So this problem here is going to be one of those type examples where we get the percent by mass information, and then we also get that molecular weight. Now, sometimes, students are clever. And it's fine to be clever. It's fine to be looking here and thinking, well, do I need to do something here? And you can actually take the atomic weight and the percent masses and figure out a way to get a formula based on that. It is, I think, a trickier way to think through the problem. I'm almost thinking of a 2-step process, though, as being the way we think of solving this problem. The way I wrote the problem would be thinking that we're going to take the percent carbon into the mass ratio. So I'm going to be thinking of starting with 84.4 grams of carbon in ratio to 15.6 grams of hydrogen, get the empirical formula first, and then from the empirical formula, use the molecular weight to get the multiples. So why don't I throw it to you guys to at least get the empirical formula, see if you can get the empirical formula. You can compare your result with your neighbor, and then see if you can figure out, and maybe you'll run out of time, because I'll give you a couple of minutes. But if you're not sure, if you get stuck on using the molecular weight, we'll for sure highlight how you use that in the second step. So see if you can get the empirical formula first, and if you can, the molecular formula second. All right, let's talk about the empirical formula. It is a trickier empirical formula problem, or at least you may have gotten to a step and then gotten a number that you're like, ooh, this is kind of tricky. So 84.4 grams of carbon convert to moles of carbon just like before, 12.01 grams per mole, 7.027 moles of carbon. Do the same for hydrogen, 1.008 grams per mole of hydrogen, that's 15.48 moles of hydrogen. At first glance, it looked almost 1 to 2. It's close to 1 to 2, but not quite. When we divide by 7.027, we get 2.2 moles of hydrogen. That's at 2.2 that we then start thinking times 2 is 4.4, times 3 is 6.6, times 4 would be 8.8, still not whole numbers, times 5, we get to the whole number. So multiply 2.2 by 5, we get 11. So 5 becomes our multiple. So a big multiple here to get whole numbers. So we need to multiply the moles of carbon and hydrogen by 5, otherwise we break the ratio. So we have to multiply both moles of carbon. So we have 1 mole of carbon in ratio to 2.2 moles of hydrogen. Multiply by 5, we get 5 moles of carbon in ratio to 11 moles of hydrogen. So that would be our empirical formula. The simplest ratio of C to H would be 5 to 11. And then we work out the empirical mass. So when we're looking at the 142.3 molecular weight, how do we use that information? That's the weight of the molecule, which can contain 1 multiple of the empirical formula, could contain 2, contain 3. It would have to be a whole number, otherwise we wouldn't have the right empirical formula. So we can take the molecular weight, divide by the empirical formula weight, the simplest ratio of those elements, and we should get a whole number. So we do 142.3, divide by 71.128, and we get that multiple of 2. In fact, I didn't do the math, I just assumed it was 2. But let's just make sure and see how close it is. It's 2.0004. So this is 2. So in other words, we have 2 of these units in one of our molecules. So our molecular formula should be C10H22. And what's C10H22 from naming? If you remember, the C10 hydrocarbon would be decane. And you can say, is that the right hydrogen count? Remember decane, just for a quick review. Decane would be C10, and then H, if we're thinking here, CH3 on the end, CH2's in the middle, 8 of them, CH3 on the end, 6 plus 16 is 22. So this is actually just the formula of decane. So you may be thinking, well, this must be some exotic compound. This is just a hydrocarbon here. So this is just a relatively ordinary hydrocarbon of decane within this example. Yeah, I think, so the question is, will there be a question like this? I mean, when you look on your daily quizzes, you'll see examples like this. You'll see, like, once you do this a time or two and get the process of the percent by mass gets you the empirical formula, then we're just dividing it into the empirical formula weight to get the units. That it hopefully will become a problem that once you practice it a couple of times, you'll see that it's not the... Oh, yeah, when you turn it into naming, no. So yeah, we won't mix this with like nomenclature. I saw a hand over here. Maybe I didn't see a hand. Okay, so these problems here are meant to show us how we get formula, how we come to know formula, or through problems like this. Of course, there's other experimental techniques. Some of them are actually much harder than this. You may think, well, isn't there some other experiment? There's something you'll learn in organic chemistry for those who take OChem, known as nuclear magnetic resonance spectroscopy. That's a way you can get structure too, but it is much more meticulous and harder than I think these examples to get your structural information. Okay, let me show you this real quick so we can see the problem that we're not going to be responsible for this semester. And the only reason I really want to make sure that we see this is because we've taught this in years past. This is the first year we haven't gone over this particular example. And I just want you to understand the nature of the problem. So, because you're going to see these in some daily quizzes, it's too hard for me to remove a question from every quiz. And I'm fairly certain they're just going to throw this back into our topic next year. So you're probably going to see these on my daily quizzes. I think we're going to scrub it off of our practice exams, so you probably won't see it there. But it's just a topic where you can take a hydrocarbon and you can burn it into CO2 and water. We know that CO2 and water are the combustion products that you should get from hydrocarbon combustion. And if you were to get the mass of CO2 and water, You could backtrack how much carbon there was in the sample, how much hydrogen there was in the sample, and this becomes another technique like a percent by mass problem. And so a problem looks like this. And I just want you to get the nature of the problem. We're not going to solve it, but I just want you to get the nature of this problem is we give you a compound, usually containing CH and O, could be a third element of any variety actually, but CH and something else. It's where we give you the mass of CO2 and the mass of water. You'll see these in the textbook too. Don't worry about solving formulas from this type of problem. Okay? So it should be doable. Maybe you could look at this and say, I could figure this out, but this is an example of a problem that we're not going to cover this semester. You'll see it at the end of section 3.5, and there's some problems you'll see in the daily quizzes that begin with forming CO2 and water from a combustion reaction and determining a formula from that information. So I just want you to see what this looks like so that you're not responsible for it. Our topic for next time will be stoichiometry, and then we'll be pretty much through chapter 3 after Wednesday's class. We'll get Friday and next Monday to do some review problems in class ahead of Monday night's exam. All right, guys, that's it for today. Have a great day.